In this video, we're going to be looking at two very important characteristics of electrical circuits and electrical circuit analysis. The first we're going to look at is current, and the second characteristic is voltage. So as we can see here in this equation in the middle of the slide, we have that our current, I, in units of amperes, is equal to dq dt, where Q is our charge in coulombs and T is our time, typically in seconds. And so I have an animation helping us understand what this equation means. So if we have some plane of observation, or I've sort of simplified it here as just a finish line, we can monitor how many charges move across that finish line, and the change in charge over some set amount of time results in our current. So basically we can say if we have charge moving through some conductor, we're going to have some current, and how much charge over what amount of time quantifies how much current we have. So more charge in a given amount of time, or the same amount of charge in less time, is going to result in a higher current. Now in this animation, I've shown positive charges moving from left to right. That corresponds to what we'll call conventional current, or typically just current, I. In reality, most of our current in most circuits comes from movement of electrons, which of course has negative charge. So if we had negative electrons creating that same current, they would be moving from right to left in the opposite direction. Typically, we don't have to worry about that, but it is worth noting that our conventional current is in the opposite direction of electron flow, and that's unfortunately thanks to an incorrect guess by Benjamin Franklin, where he assumed that our current was due to positive charge carriers. So now that we have this idea of current, we can relate that back to our circuit elements that we talked about in the previous video. So here, if we have a resistor, it in a circuit might have some associated current. So this blue arrow and this I of t shows our reference direction for our current through the resistor. So the idea of reference is going to be important later on when we talk about something called passive sign convention. So our second key characteristic that we're going to look at here is our voltage. Our voltage in volts V is equal to dW dQ. So the textbook uses a W to represent energy. So we want to be careful to not get that mixed up with a unit that we'll see later on. So the script W is energy divided by dQ, where again the Q is our charge in coulombs. So I forgot to mention our energy typically is going to have units of joules. So by definition, there's not as intuitive an illustration, but voltage is the work or energy required to move a charge between 2 points. So if we go back to our simple resistor, we can say we have two ends, A and B. Then we would have some voltage across that resistor in a circuit, and we would have a positive polarity. In this case, I've drawn it at A, and a negative polarity. In this case, I've drawn it at B. So this blue plus and minus gives us our reference polarity of the voltage across the resistor. So in the previous slide, note that we had current through a resistor, and here we have voltage across a resistor. Another important thing to note about voltage is it always has to have 2 points as we're talking about it. We have to have some reference point. In this case, I'm referencing to B, so I could say the voltage at A with respect to B. So that's why this A comes first in the subscript here in the V sub AB. One sort of easy analogy that can sometimes help with that is we can think about height, right? So if we're talking about, for example, the height of different buildings, so here's a simple building with some windows, or a tree, or a mountain, or a person. So maybe we put a little person over here too, right? So we have a person like that. So forgive me as I'm drawing with my mouse here. It's not looking great. But if we're talking about the height of the building, we would reference that to some point, the ground that it's constructed on. The same way if somebody is standing here on this ground, we would reference their height to the ground. So the same way that we have to have a reference point as we're talking about the height, we have to have a reference point, in this case point B, as we're talking about the voltage.